In this video, we'll be discussing how to implement simple linear regression using matrices. Now we're going to start with a matrix review, and if you haven't had linear algebra, don't stress too much about this. The big things that I want you to take away from lecture 6 are primarily how we in general construct these things and how they are very closely related to the univariate methods that we've used previously. So first of all, we're going to be using matrices. And the reason that we use matrices is to simplify the regression, not for simple linear regression, but for extensions that we will discuss in the next chapter. That specific extension that we're going to be discussing in the next chapter is including multiple predictor variables. Now, writing this out by hand in terms of a model is not particularly complicated, but solving for the least squares solutions when we have multiple different betas, a whole bunch, let's say we have another predictor, so we have beta 0, beta 1, and beta 2, or increasing the number of betas we have, etc., that becomes a little bit more complex. In fact, that actually becomes fairly complex if we try to just do it by hand. So what we're going to end up doing instead of doing it using scalar notation, that is just using numbers, now we're going to represent the models using matrices, which is going to simplify a lot of the calculations. But again, we're going to start with a review. So a matrix is a rectangular array of elements. So you think of number, 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 then another row, number, number, number. Matrix is just a grouping of numbers, and so we can have R rows and C columns, R for row, C for column. Sometimes you'll see this as capital I rows and capital J columns, so you'll see it either way. Matrices are typically denoted in writing when I'm writing on the computer by capital bold letters. So when you see that, just note that that's what's going on. And then given elements of that matrix tend to be denoted by lowercase letters, and we use subscripts to tell which row and column we're talking about. So for instance, capital X bolded might be the matrix X. This could also be a vector X. Bold is non-specific. It just means it's not a scalar. It's not a single number. It's something more. Whereas the lowercase x sub ij, it lets me know it's a matrix because I have two indices, a row and a column indices. If I just had one, then so x sub I, it would be a vector. And because it's a lowercase with indices, this lets me know that this is actually an observation from this larger matrix. So this lowercase x and this capital bolded x are connected. Capital bold X is the matrix X. Lowercase x sub ij is the ith row, the jth column observation from that matrix. Now, when we're writing this out by hand, so if I were doing this like on a whiteboard, I'll, instead of bolding, because I can't really bold when writing things out by hand, I'd write X with a little twiddle underneath, or whatever that's called, a little tilde underneath to indicate a vector, and then I'd write two tildes underneath to indicate a matrix. And in general, the number of tildes underneath indicate the number of dimensions. So one tilde would indicate that it's just one dimension, and as we talked about before, that's going to be a vector. Two tildes would indicate that it's got rows and columns, so that's going to be a matrix, and then three tildes would indicate tensors, and so on and so forth. All right, so for example, X sub ij, capital I, capital J, is a matrix with capital I rows and capital J columns. This subscript, I'll try to write out, and we'll talk about this in a sec. I won't do it for all of the matrices because a lot of the matrices that we use, we do know the dimensions. But in a capital bolded matrix notation, the subscript represents the total dimensions in the matrix. So capital I rows, capital J columns. In this case, I see there's capital J columns, and then I see all of the different indices. And you can take a look at this for a while if you want to try to get a feel for what's going on. How as I go down one row, the first number changes from 1 to 2, and then I go on until I get to little I, and then I keep going on and on. The last entry is capital I, which is the total number of rows. And then as I change columns, I the second number changes, not the first number. It goes from 1 to 2, and then goes on until it turns into J, and then goes on until it turns into capital J, which is the total number. Now, of course, this little j and this capital J are numbers, right? In fact, this little j is just meant to help you realize what's going on. You're never going to have a observation in your row with an actual x sub 1j. This is just going to be numbers until you get to the capital J number of columns that you have. So again, for a while, I'm going to try to put the dimensions in as a subscript. Textbook has them underneath. You can have them either way, really. So for example, capital X sub 2 by 3 is a matrix having 2 rows and 3 columns. But as we go through the course and we start to see these matrices that get repeated over and over, I'm going to stop doing this just because it's not really needed. So a matrix is called a square matrix if the number of rows and columns are the same. So recall that I can have a different number of rows and columns, but if they're the same, then my matrix is square. That is, the number of the kind of the length and the width are the same. If I look at the little matrix box, and that's the definition of a square, so we call it a square matrix. Now, most of the matrices do not at all have to be square, but we will deal with a couple of matrices that are square. One particular square matrix of importance is something called the identity matrix. The identity matrix has ones on what we call the diagonal. If you just trace a diagonal from the top left to the bottom right, that's your diagonal. It's a little bit more complicated. It's not as straightforward on non-square matrices, but on square matrices, diagonals aren't too bad. Just trace from the top left to the bottom right. That's called the diagonal. Incidentally, the bottom left to the top right is called the off diagonal. We won't talk about that. But the identity matrix is a matrix of all zeros except on the diagonal, which is entries of ones, and we'll talk about that later. A column vector is a matrix that only has a single column. So vectors are, again, just have one dimension. So the question is, which is the dimension? Is it a column or is it a row? And a column vector is a matrix that has only a single dimension in the column direction, and a row vector is a matrix that has only a single dimension in the rows. Typically in this course we'll just talk about vectors more generally, but column vectors and row vectors can be very useful when describing the dimension of matrices for matrix multiplication. Now transpose, when we take the transpose of a matrix, we kind of flip it on its head. Now first of all, the notation for transpose is either going to be a little tick mark or to the t. This is not to the tth power. This indicates a matrix transpose when used with a matrix. So what we end up doing is we take the matrix form, and all of the columns become the rows. So this first column of all ones becomes the first row of all ones. The second column, 3, -2, 4, 1, becomes the second row, 3, -2, 4, 1. The third column, 0.3, 0.7, 0.5, 0.5, becomes the third row, 0.3, 0.7, 0.5, 0.5. So what it's like is if you folded this matrix over, like you grabbed it like a sheet of paper and you took this bottom left corner and folded it over to the top right, that's kind of what this ends up giving you. But if it makes more sense to you to think of all of my rows all of my columns are becoming rows. Incidentally, all of your rows become columns. That saying both things is the same. So whichever way this works out for you, please think about it that way. But for me, it's easiest to think about, again, looking at this like a little sheet of paper, and then I grab the bottom left corner and I fold it to the top right, and then I've got all my ones are now going across. My 3, -2, 4, 4, when I fold this over to the top right, is the second row, and then if I fold my sheet bottom left to top right, my 0.3, 0.75, 0.5, 0.5 is all in the bottom. So that's how I tend to think about it. And matrix transposes we will use pretty heavily in the mathematics that we're going to be talking about with simple linear regression. Now, sizes of matrices have to be identical so that we can add or subtract them. So let me show you, if we have our sizes identical and we're adding two matrices, I literally just add the corresponding elements. So the first column, the first row, to the first of the first matrix, first column, first row of the second matrix, gives me the first column, first row of the result. the, let's see, what is this, second row, third column of the first matrix plus the second row, third column of the second matrix gives me the second row, third column of the result. So this should hopefully make sense in terms of adding and subtracting matrices. It's pretty straightforward. What's also straightforward is if we multiply a matrix by a constant. So scalar just means it's like a regular number. It's not a matrix. So when you hear me talk about scalar quantities, it just means it's a regular number, not a matrix. So when we multiply a matrix by a constant that's a scalar, we simply multiply each of the elements by that number. So for instance, one of the computations we'll do later in the class is take sigma squared, our estimated error, our population error, and multiply it by the identity matrix. Recall the identity matrix of 3 by 3 is a square matrix with all the diagonals, or everything 0 and all the diagonals are 1. And then we take the sigma squared and we multiply a matrix by a scalar. All we do is we multiply each of the elements in the matrix by that scalar. So sigma squared times 1, sigma squared times 0, sigma squared times 0, and then the result is that multiplication. Now anything times 0 is just 0, but sigma squared times 1 leaves me with sigma squared. So this matrix will look like sigma squared on the diagonal of every, sigma squared on all of the diagonals. And again, this is going to be constant because this matrix can be a little tedious to write out. Actually, what you're going to see in place of that matrix is this notation on the very left-hand side. So feel free to come back to this slide if you want to when we start getting to work in the simple linear regression in matrix form. All right, now multiplication of matrices is a little bit more complicated than these things. Recall that with the addition, you just add kind of straight across, kind of like what you would think with multiplication by scalar. It also hopefully kind of makes a little bit of sense. Multiplication of matrices by each other is a little bit more complex. So first of all, and actually shame on me, I don't think, oh, here, I do mention on this slide. So the element ij is what we call the sum product of the ith row and the jth column. And we will talk about what this means in just a second. Now, one big requirement that we have here that we didn't have previously is that we require the number of columns in the first matrix to match the number of rows in the second matrix. So this is just a definitional thing. If I'm multiplying two matrices together, I ask a question, is the number of columns in the first matrix the same as the number of rows in the second matrix? If it is, I can go forward. If it's not, then I have to stop. So this is a rule to kind of write down and be aware of. And actually, even when we're working on some of these problems in R, there's a common error that you can get in R. You'll get something like a non-conformable arguments error when working with matrices in R. That often comes back to this rule. So this is a good one to write down and remember and practice going through when multiplying matrices. Is the number of columns from the first matrix the same as the number of rows in the second? Now, one weird thing in multiplying matrices is that A times B is not the same as B times A. And actually, one of these is usually going to be undefined, because what ends up happening is that the number of columns in the first matrix may be the same as the number of rows in the second matrix, but if I flip-flop the order, now the number of columns in the second matrix has to be the same as the number of rows in the first matrix if I did B times A, because I'm changing the order, and that's a problem, and that's not always true. In fact, it's relatively rarely true. So we want to make sure that these things do match up so that they can be multiplied together. And because of that, and because of this rule, we have this kind of weird property that A times B isn't always the same as B times A. And in fact, again, A times B may be defined, whereas B times A may not, or vice versa. All right, so you can use this if you want to. In general, the dimensions of the product, if A is I by J and B is J by K, then the dimensions will be I by K of the product. Notice here that, again, the number of columns in the first matrix should be the same as the number of rows in the second matrix. And actually, this is a little mental trick, is if I write out the dimensions Ij of the first matrix and the dimensions Jk of the second matrix, this inside number should be the same for both, and the outside numbers, I and k, is the dimensions of the final product, I by k. Now, one thing that we're going to do very, very, very commonly is take the product of a matrix and its transpose. So if a matrix has dimensions of n by p, n being eventually the sample size, p being the number of parameters, which will be the number of independent variables minus 1, then we will have a p-dimensional square matrix if we do x transpose x. While I want you to kind of get a feel for the multiplication operator, honestly, you're never going to be given this on a test or anything like that. So don't stress too much about it for this class. Maybe save it for a linear algebra class, and you can think about it more then, because we're going to be using a computer or calculator to multiply large matrices. This said, computers or calculators will throw you errors if you do not understand the rules of matrices that we talked about in the previous slide and this slide. So it's important to understand everything that I just talked about and to be able to understand it deeply enough such that you could multiply matrices on your own. That's how well you have to understand this in order to consistently get a computer to do this for you. Because if you don't understand it to that degree and the computer throws an error, you're not going to be able to troubleshoot where the error is falling. So please do make sure that you are understanding where we're coming from when we're talking about this and understanding all of the rules about matrices. Okay, so let's do an example. All right, so what's going to happen is I'm going to multiply the first row by the first column, and then and that's going to be the first entry, first row, first column entry in the final matrix. Then I'm going to multiply the first row by the second column, and that's going to be the first row, second column entry in the final matrix. Then I'm going to multiply the second row by the first column, and same thing, that'll be the second row, first column in the final matrix, and then the second row by the second column, that'll be the second row, second column in the final matrix. Now, if this seems complicated, again, it kind of is a little bit more complicated, but what ends up happening is, and after I multiply these, I'm going to multiply element-wise, which means I'm going to take this first entry, multiply it by the first entry, this the second entry, multiply it by the second entry, this third entry, multiply it by the third entry, and then I'm going to add all of these things up. So that's the one thing I forgot to mention, is after I multiply this first row by the first column, I then add up all the different elements. So 1 times 1 plus 1 times 1 plus 1 times 1 is the first row and first column of my final entry. So what ends up happening is I take the rows of the first matrix and I take the columns of the second matrix, and by combining these, that's how I get the final matrix. So I take, to get the first row of the final matrix in the second column, I take the row from the first matrix, the column from the second matrix, and I multiply them together. 1 times 2 plus 1 times negative 1 plus 1 times 5, which is 2 minus 1 plus 5, and that's my final entry in the first row, second column. Now for the second row, first column, I'm going to take the row from the first matrix, the column from the second matrix, second row, first column, and then multiply them and add them together. So row from the first, column from the second, row 2 times 1 plus negative 1 times 1 plus 5 times 1 gives me 2 minus 1 plus 5. And that's my entry for the second row, first column. Then finally, I'm going to take the, for the second column and the second row, I'm going to take the row from the first matrix again, the column from the second matrix again, multiply these together and add them. So row times column, 2 times 2, row negative 1 times column, negative 1, and then 5 times 5, and that gives me 4 plus 1 plus 25, negative 1, negative times a negative is a positive. So 4 plus 1 plus 25. And then I would calculate these addition problems, and this ends up being my, my matrix. Notice, incidentally, how these are transposed of one another. If I took the bottom right hand of the matrix and I flipped it over, or the bottom left hand and flipped it over to the top right, I would turn this first matrix into the second matrix. So this is kind of like X transpose X, or XX transpose. All right, so a matrix in general is said to be symmetric if it is equal to its transpose. So matrices, such as X transpose X, will always be symmetric. So if I multiply X transpose times X, this is always going to be a symmetric matrix. Now, a matrix is called a diagonal matrix if all of the off-diagonal elements is 0. So we talked about the identity matrix earlier. So the identity matrix is a diagonal matrix. Now, diagonal matrix, the on-diagonal elements don't have to be 1. If they're 1, that's the identity matrix. Diagonal, they could just be anything. But in a diagonal matrix, everything that's not on the diagonal is 0. Interestingly, regarding the identity matrix, if I multiply anything by the identity matrix, by the appropriately sized identity matrix, nothing will change. So this is kind of an interesting factor of the identity matrix, and why we like the identity matrix is if I multiply a particular component or a particular vector or a particular matrix by the identity matrix, I will get that original vector or matrix right back. Now, the inverse of a matrix is denoted that matrix to the -1 power. And what ends up happening is that if we have the inverse of a matrix times its inverse is the identity matrix. Now, the inverse only exists if the original matrix is square and full rank, and rank just means that the matrix is the maximum number of linearly independent columns, so that we don't have two columns that are just copies of each other, or where one column is just another column multiplied by a scalar element, or could be created from a combination of other columns. Now, inverses actually are kind of complicated to put together in this course. I don't think we're going to do an inverse by hand. We're just going to use the computer to calculate inverses. And R has a handy feature called solve in the program that will calculate inverses for us. Now, we've talked a lot about the construction of matrices and the different kinds of matrices that we can have and the different operations of matrices that we can have, talked about inverses of matrices. But another big component that we have in regression is this idea of randomness. So we can have random vectors. Suppose that the vector u, where it's of dimension n by 1, so this is a row vector. This is a column vector, is a random vector. Then each of the individual u sub i's is a random variable. So if I have a whole bunch of u's listed down in a column, and we call this whole vector random, then each of the observations within the random vector is itself a random variable. Now, the expected value of this random vector is another vector, and the expectation of the vector itself actually is just the listings of the expectations of each of the elements in the vector. Recall that expected value is just the mean, except under random variables, it's kind of the mean of the random variable. Now, that each of these elements in a vector, and again, I want you to just think of this long list of numbers, and if we call this a random vector, then each of the numbers in the vector are random. And what we say is that if I wanted to take the mean of the vector, then I could find the mean of each one of these little random entries in the vector, and that each of those random entries, because they're random, any random variable has a mean, so we could find those random values. And because they're random, they can also have variances and may have covariances between the different pairs. That is, not only may something vary on its own, but something may have a relationship with another data point. Now, this brings up an important idea called the variance-covariance matrix. So in general, for any set of variables, and again, think of all these listed in a row, the first one, the second one, all the way down to the nth one, the variance-covariance matrix is listed as this, and this is an important idea. This is a very, very, very important idea, fundamental to how we approach regression in matrix form, is this concept of a variance-covariance matrix. Now, what we're looking at is we're looking at the variability of the first observation And then we're also looking at how do the first observation and the second observation relate. So the sigma squared of mu1 is the variability of the first observation. You could look at it. Sigma squared of mu2 is the variability of the second observation, and then all the way down. So the diagonal elements are the variances of each of these different random variables. So the variances of each of our observations. So if I think about, in class, we've talked about kind of an overall variance for all of our data, but here we're actually indicating that each of our data points could have its own distinct variance, and that's what we're discussing here, is that each of these diagonal elements are the variances of each data point individually. Now, also, the data points could relate to one another in what's called a covariance. So as one variable increase, it's kind of like think of a correlation, actually. A covariance is an unstandardized correlation. So I could not only have the variance of each of the data points, but I could have correlation between each of the data points. Now in regression, we said, oh, we don't want data points to correlate in ways that aren't included in the model. So that would be a bad thing. That would indicate lack of independence. But in this case, we can account for the fact that the data points could correlate between each other, and this is where we do that, indicating the covariance between the different data points. And again, covariance is a fancy term. You can think of it as a unstandardized correlation. So when we're dealing with uncorrelated data, that is our independence assumption, the covariances are zero. So all of these relationships between data points that could exist here that we were talking about earlier, all of these are zero. The only thing that we have is the variance of our data points. So what happens when the covariance is zero is all of those off-diagonal elements turn into zero, and that becomes the definition of a diagonal matrix. The random variables will also be uncorrelated. So again, this comes from the fact that when our covariance is zero, covariance is just an unstandardized correlation. But if the covariance is zero, then the correlation is going to be zero. So when we say that the variables or the off-diagonal elements are related or have a number, then they are automatically dependent. And again, this violates our assumption of independence. Now, random variables can be dependent but uncorrelated, and this comes from the fact that our correlation looks at linear dependence. So recall how we discussed the difference between linear relationship and nonlinear relationships back in the very, very first chapter in correlation that we discussed. Now, normal random variables are a special case. If we have a lack of correlation, this does imply independence, at least for the sake of our arguments in this format. All right, now this has concluded our discussion and review of matrices. With all these tools, we are ready to jump into the next section, which is the matrix equations for the simple linear regression, where we're really going to focus not as much on the matrix arithmetic again, but on the format of the equations and understanding how the equations fit together.